Alright guys, let's get started. What's loud? So today we continue our discussion of Bayesian methods. And well, the last homework will be on Bayesian methods. One particular, it's very loud and echoey. Do you guys, is it bothering you? Yeah, it's a little bit too loud. I'll turn it down. Is this better? Let the expert do it. All right, so I'll just keep talking and so the next homework, the last homework, we'll be dropping the lowest homework grade. So if you've done all well on your homeworks to date, then you can skip the last homework. I think it's good, good stuff. If you really don't want to do it in the summer. It's good for you. It'll be on the beta binomial model for Bayesian statistics, which is about as simple as it gets, but then again, we go pretty deep into different ways to deal with it. So some stuff about empirical Bayes and hierarchical Bayes. So I think it's worth a look. Okay, good? Good? Okay. So we're continuing on with Bayesian methods. We're going to talk about Bayesian regression for the first part of today. And then later we're going to get into some intro to clustering. We'll talk about k-means, which I think most of you have heard of, and then mixture models, starting Gaussian mixture models. And tomorrow we'll hopefully finish up with Gaussian mixture models with also a general treatment of the EM algorithm, which would be worth preparing for. I'll give you some notes in Piazza on what might be some good little math to review for that. OK, let's start. So first, a brief recap of the Bayesian statistics setup. In Bayesian statistics, what the data scientist starts with is two things. One is a likelihood model, which would look like this. If D is our data, this gives us the probability or the likelihood for an observed data set D conditioned on some parameter theta that we don't know, theta in some parameter space. And so far, this is the same as frequentist statistics. What's special in Bayesian statistics, what's different, is that we also consider theta to be a random variable. And moreover, we put a probability distribution on theta. That's also the data scientist's job before even looking at any data. It's called a prior distribution. Prior meaning before any observations. So we have this likelihood model, which gives us likelihood of data given the unknown theta. And then we have the prior distribution, P of theta. You put them together, and you have a joint distribution on what? The and the. Exactly. You have a joint distribution on the data and the parameter theta, right? OK. Good. So in this setting, is there anything that's unknown? What do we mean exactly? Are there any unknown parameters? What? So we have a full joint distribution on theta and the data D. There are no parameters to tune. There's no, in some sense, there's nothing that's unknown, unlike in a frequentist setting where we leave theta as something that we have to fit. And it's a subtle difference. OK. So we set up our prior, we set up our likelihood, and then the thing to do is compute the posterior distribution on theta, given the data D, which we write P of theta given D. Finally, we may want to take some kind of action. Maybe it's predicting your best single guess for theta, whatever it is. You can base that action on the posterior distribution of theta given the data, which summarizes all the information that we're able to extract from the data pertaining to the parameter theta. OK, so examples of actions you might want to take. You could look at so theta, after we observe the data D, we can come up with a distribution over theta. That's the posterior distribution. And then we might produce as an action the expected value of that posterior distribution. That would be a single number or single value. You could produce an interval AB that we think contains the random variable theta with probability 0.95. This is the Bayesian analog of a confidence interval. So different things you can produce as actions. All right, so the posterior distribution, just recount this simple application of Bayes' rule. And there's a few objects here that go by names that we're going to talk about a lot. This is the posterior on the left. P of d given theta, that's the likelihood. P of theta is the prior, and P of d, that's the marginal likelihood. Okay. So just to note that the posterior distribution is a distribution on theta. It's a function of theta. You plug in a theta, and it tells you the likelihood or the probability, right? So this denominator P of d is independent of theta. So it's just like a scaling constant. So we really can write just the distribution on theta, the density of theta is proportional to the numerator. We can drop the P of d. It's just a scaling parameter. If we wanted to get it back, how do we find what P of d is? P of d, yes. P of d, first of all, what kind of object is it? It's a number. P of d is a number. And we know that the integral of this distribution over theta has to be 1, this function over theta. So you could integrate the numerator, and you know that has to equal to P of d. Okay? So that's how you can recover it. All right. So summary on the Bayesian approach. We come up with a prior that represents our beliefs of theta before we look at the data d. Then we see the data d, and the posterior distribution gives us some kind of most rational updating of our belief on theta. It's kind of an interpretation of this Bayesian approach. And then we base all of our actions on this posterior distribution on theta. OK, good. So last week we talked about coin flipping. Remember the beta prior and the binomial distribution, and we were trying to estimate the probability of heads. Today we're going to talk about something that's perhaps more practical, or at least also very useful, which is linear regression in a Bayesian setting. OK, so Bayesian conditional models. Now we're back in kind of a predictive setting where we have an input space and an output space. So our input space, as usual, is RD. Output space is reals. And now when we write down our likelihood model, or we could call it a conditional probability model, before it was just P of y given theta. Now we've put the x in the conditional, right? Because we're going to predict the distribution of y given an input x. It's kind of a regression setting, input to output. All right? Great. And when we say conditional probability model, we're saying that we're conditioning on the input x. The fact that the theta here, that's not what's being referred to by conditional in that term. OK. So in these conditional models, you'll see at every step in every equation, we're always conditioning on x. It's essentially equivalent to assume that x's are all known, that they're not even random. When you condition on something, that assumes you know what it is, and so it's as though it's not random, it's just a fixed number. So throughout, it's safe to assume that everyone knows x's, everyone knows what the x's are, and you don't have to really treat them as random variables. Sometimes we'll put them in the conditioning, sometimes we won't. OK. So of course, we have the conditional probability model, and then we still have the prior distribution on theta. So that was a general conditional model. Now let's get specific. Let's talk about the Gaussian regression model. We've seen this before. Latent presented this in a lab. This is when we were predicting conditional distributions, given x, produce y, and we assume that y is Gaussian. We're repeating that now. So here's our model, our likelihood model. The distribution of y, given an input x, and given this parameter vector w that's unknown, the distribution of y is Gaussian with mean w transpose x and variance sigma squared. OK? So this should look familiar to you. We've had the same thing before. The only difference is that now we're going to put a prior on w instead of trying to estimate it with maximum likelihood. Right? So before, when we've had this set of models, we can compute, given our data, we have all these x and y's, we can compute the likelihood of the data we've observed by multiplying a lot of Gaussian densities together. And then we could find the w that maximizes that likelihood. And that would be our maximum likelihood estimate of w. And if we wanted to predict a distribution for y given x, we would predict Gaussian w transpose x. Any questions on this? Familiar? All right. So what's just a quick concept check. What's the parameter space here so far? What's tricky? I didn't really say if we're in the Bayesian setting or not. If in the standard setting where we're talking about having parameters, the parameters would be W. If this were the frequentist setting, the parameter would be W. The parameter space would be RD. Okay. So we have some data. We're going to use some notation that's convenient here. We're going to use y without a subscript to mean the vector of all the y's, and x without a subscript to be the vector of all the x's. D would be the set of the pairs. Okay. Yeah, thanks.
Why is W a parameter, but a sigma is not a parameter?
So sigma squared, I've assumed we know sigma squared. This is just the model that we've defined, is that W is unknown, but sigma squared is known.
As it's a regression model, so why don't we like making the sigma more smaller that is more better, like wiki and more precise prediction on this?
Yeah, so you could say, what if we don't assume sigma squared is known, and we tried to fit sigma squared and W using maximum likelihood? You absolutely could do that. And then you are also asking, would that be a problem? Would the maximum likelihood estimate for sigma square go to 0? Are you asking that? Say again.
So that's the method.
Yeah, so the maximum likelihood would try to be 0, but that would actually only be the case if all of the data points were exactly on a line. And so if, for instance, you have only 2 data points, then indeed there would be no maximum likelihood estimator, because you would make the likelihood always ever bigger if you make sigma squared smaller. But if the points are not collinear, then you wouldn't be able to find that wouldn't be the case. Good question. Any more questions? All right. OK, and we're assuming the yi's are conditionally independent given the w's, as you might expect. OK. So Gaussian likelihood of y given x. Let's work out those details. So now y is the vector of all of our observed values y. So by the conditional independence, we can write this as a product of the individual probabilities, likelihoods of the individual observations, yi, correct? Clear. OK, great. Now we just plug in our model, which is that the conditional distribution of yi given xi is Gaussian with mean w transpose xi. Look at this for a moment. OK. Any questions on where this is coming from? OK. All right. So now, I claim that you should be able to see in your head that the maximum likelihood estimate for this is something very familiar. So how would we find the maximum likelihood estimate of W in this scenario? What have we written down? We've written down the the likelihood of our data. This is an expression for the likelihood of our data. The maximum likelihood estimate would be, let's maximize this expression over what? What parameter? W. We'll find the W that maximizes it. OK. Yeah, exactly. Here, mean squared. Y. Let me take the log of this. This breaks into the sum of constant, the log and the x cancel, and you get the sum of negative yi w transpose xi squared. It's like the negative sum of squares. So we're trying to maximize the negative sum of squares. That's like minimizing the sum of squares between yi and w transpose xi. This is just least squares regression. Cool? All right. Just to review. All right, so now we get into the Bayesian approach. So far, this Gaussian likelihood, all this stuff, we've talked about maximum likelihood. This is not Bayesian yet. Now we make it Bayesian by introducing a prior on W. So W now goes from being a parameter to being something like, to being a random variable in our setting. So we introduce a prior distribution on W. Let's keep it simple, and let's have a Gaussian prior on W. Say mean 0 and covariance matrix sigma 0. For now, it could be arbitrary. We want it to be positive definite. All right. I chose 0 and sigma 0. These are not unknown. They're known. I fixed them. It looks like a variable, but that's a specific matrix. All right. So this is a fixed distribution on W. Okay. Posterior distribution then is Py given D. Let's break that out a bit. All right. So W given xy, we can use Bayes' rule and flip the y and the W. So we've done there. Okay. We can drop, what can we drop for proportionality? P of y is independent of W. So that becomes like that. And so the first line here is the likelihood. That's this piece. And then what do I have to add to get the equality? The prior, that's P of W, which is Gaussian density on W, like that, right? So this is an expression, an explicit expression for the posterior distribution of W given the data D. All right, that's neat. So the question is this something simple or complicated? Right now, it looks like the product of of a bunch of Gaussian-like things. Does that simplify or not? We'll come back to that. Okay, so we have a posterior on W. What can we do with it? What's interesting about this? What does it give us? All right, so suppose we knew W. All right, I tell you W. Take a look at our likelihood model. What would you say is the best prediction function I can give for Y? So given X, what's the best prediction I can give for Y? I tell you W. Moreover, you know how the data are generated, because we're assuming I also give you the likelihood model. So what would be the best prediction for Y given X? Say again? Yeah, the expected value of Y given X is actually often called the regression function. And that will be optimal in certain situations. In what situation in particular? Okay, if we're trying to minimize the expected square error between our prediction and the actual value, then indeed the conditional expectation of Y given X minimizes that. That's right. It also minimizes a few other loss functions, but the square loss is what we focus on here. Great. So if I told you W and we were trying to be optimal for square loss, then yeah, you should predict the expectation of Y given X. Excellent. What's the expectation of Y given X? Say again. The sample mean of what? First, conditional expectation of Y given X, say. Great, that's right. So the distribution of Y given X and W is Gaussian with mean W transpose X. The expectation of Y given X and you know W is the mean. That's W transpose X. So the best you can do is predict W transpose X if you know W. All right. We don't know W. What do we have on W? We have a probability distribution on W called the posterior distribution. It's our best guess as to the distribution of W. It's our belief, represents our belief on W after observing the data. Okay. So let's catch up on the slides. So this distribution on W effectively gives us a distribution on prediction functions. For every W, we have our best prediction function that we can use. So we have a distribution on W that gives us a distribution on prediction functions. In fact, we started with the distribution on prediction functions too. We started with the distribution on W, right? That was the prior. So the prior distribution on W corresponded to a prior distribution on prediction functions. And the posterior distribution on W is a different distribution on prediction functions. All right. So far we have a distribution on prediction functions, and we'll see what we can do with that in a bit. But let's take a quick example to see some visualizations of what we have so far. All right. Simplest example. Input space is just the interval -1, 1. All right. And output space is reals. And let's take our linear model this is a one-dimensional input space, right? But we're going to have a bias term. So the output y, this is the true data generating model. Y is equal to W0 plus W1x plus some noise term epsilon. Epsilon has a Gaussian distribution with 0 mean and a known variance. All right. So what's the likelihood model for y? Y given x and w is very good. So the distribution of y given x and w is y given x and w, 0 and w1 is Gaussian with this as the mean, and this is the variance. Because w0 plus w1x, that's just a number. You add to that a random variable that's normally distributed with mean 0. That's just going to shift the mean of this Gaussian distribution to w0 plus w1x. Is that clear? Good. Okay. So this is how the data was originally generated. This is this is exactly the same thing, just another way to write the model of y given x and w. All right. I keep writing what's the parameter space, but I don't really mean that here. Well, I could. I didn't make it Bayesian yet. So if this could still be a frequentist approach, w could be parameters, in which case it's R2. But I think I'll change that on the slides. All right. For prior distribution, we'll put a simple Gaussian, mean 0, and I is the identity matrix, so just two independent Gaussian distributions on W0 and W1. Yes, please. No estimates. There are no estimates. My prior is censored at 0. Why did I choose that? That's data scientist's choice. If you have an idea of what you think W will be centered around, use that. Usually we don't. And if you do, you can usually center the data in a way that your best guess at W is back to 0 or something. That's right. What's with the half? I had to. You have to pick something to generate. You have to pick something. So, what does half I represent? It represents your uncertainty in W. So, in some sense, a half I. So, what is this? Standard deviation is roughly is. Well, it depends if that's the variance or the standard deviation. But let's just say it's the standard deviation. So, I'm saying I think W is, centered, so I'm going to say mean 0, and the range of expected values that seem reasonable to me is something like a half, plus or minus a half. So it's kind of sets the scale of W. I think it would be very unlikely that the optimal W0 and W1 are like 100, right? So the variance sets the scale of what I expect W to be like. That's a good question. Say again. Uniform distribution on W0, W1. You can choose any distribution. It should represent somehow what you think are reasonable values. Another reason to choose a particular type of distribution is because it makes certain calculations much easier. So the choice of the Gaussian here was not a coincidence. It's going to make all the calculations come out very simple and in closed form. The Gaussian is called a conjugate prior in this setting because we'll find the posterior distributions are also Gaussian, and we can explicitly write down all the posteriors. If you used a uniform prior, definitely wouldn't be the case, and you could still use it, but everything would have to be done like numerically with numeric calculation and integration or simulation or something like that. Yeah.
Are W0 and W1 two separate distributions?
W0 and W1 in general can have a joint distribution with each other. In this case, it's Gaussian with a diagonal covariance matrix, so they're independent. Does that answer your question?
Is W one distribution and you draw two samples from the distribution X?
No. Okay. W, first of all, W is a vector of two numbers, W0 and W1, two random variables, W0 and W1. And, oh, I see. I think I see what you're saying. So this is a Gaussian distribution on pairs of numbers. This is a two-dimensional Gaussian distribution. You can tell that because it has a covariance matrix I. Because I was saying, is a 2 by 2 identity matrix. Some more questions? It's a good point to ask some questions. We're about to see some pictures. OK. All right, and if you knew W, the best prediction you could have, yeah, please. So, great question. The question is, does your prior distribution matter if the sample size goes to infinity? Let me capture it that way. And the answer is, if you do the prior right, no. You have to be careful that the prior gives some likelihood to every possible parameter value that might actually be true. All right. So, if you use the uniform distribution on -1, 1, -1, 1, the box, then you can never have a posterior that has any weight on something that's not in that same box. Okay, you can have different amounts of weight there, but if your prior gives 0 probability to a particular point in your space, then the posterior will also have 0 probability. You can't get away from 0 probability or 0 likelihood. So, but except for that, yes. As long as, in our case, the Gaussian distribution has full support, in other words, it's greater than 0 everywhere, then the posterior will be independent of the prior as the sample size goes to infinity. Yeah. And it converges to what you want it to. That's a separate course. Okay. So let's think about the prior first. On the left, we have a picture of the prior distribution on W0 and W1. X-axis is W0, y-axis is W1. Remember, we have two unknowns here that we're interested in, W0 and W1. You see it's censored at 0. And OK, this is a heat map for a Gaussian distribution. What do you think is going on the right? The axes are x and y. We have all these lines. Say again. WTX. Yeah, basically. So these are prediction functions corresponding to different W's. The W's are how did I generate these W's? I didn't. I got it from a book. How did they generate it in the book? Say again? OK, in this case, these W's are coming from the prior distribution. OK. We've actually re-implemented this in Python. This original code was, I don't know, and then, do you guys know Kevin Murphy? Yeah, we used his book last year. So he re-implemented in MATLAB the code to make these pictures. And then this past summer, we re-implemented it again in Python. But I didn't copy the new pictures here. So this is still the old pictures from Bishop's book, in case you're interested. All right. So, yes, on the right, this is expectation of y given x and w. This is our best prediction of y given x for many different w's that were chosen randomly from the prior distribution. All right? So before seeing any data, remember we have a prior on w. Every w gives us a prediction function, the expectation of y given x. And that's what's being drawn here, the prediction functions for many different w's. All right? Great. Now let's look at some data. So this is after one observation. After one observation, we can update our prior and get a posterior distribution on W. The posterior distribution on W is what we see here. So it's not spherical anymore. It's become elliptical. Right? right. And on the right is what now? Now we've sampled W's from the posterior distribution after one observation. That's W's coming sampled from this distribution. And you'll see that there's a lot more uniformity to the prediction functions now than before. This is the prior, and this is the posterior after one observation. Oh yeah, thank you, yes. The blue circle is the single data point that we observed. So it's neat that in Bayesian statistics, because of the prior, that without any data, we already had prediction functions, right? From the prior, we had prediction functions. We have prediction functions from one point as well, and they're already a little bit better. It wouldn't really make sense in a frequentist setting to do linear regression on a single data point. Maximum likelihood would not be interesting at all, right? There is no maximum likelihood. There's infinitely many lines that go through a single point. Yeah? How do we get the posterior distribution from the prior distribution? Just by observing one point. Just do it. You write down the. Here, let's just take a quick look. Well, here it is. This is the posterior distribution, and where in here might there be an issue for only having one data point? What happens when you have one data point? This is the posterior distribution for an arbitrary data set D. If you have one data point, this n is 1. So you have the product of a single Gaussian and another Gaussian. So it's OK, and that's what it is. Any questions on this? Good. All right, let's do some more points. So here's 2 observations and then 20 observations. And you can see these are the 2 data points. Here's the 20. You could see the posterior distribution concentrating on a particular vector W. And the prediction functions become much more uniform. Yes? OK, interesting question. Why are we bothering plotting a whole distribution of prediction samples from a distribution over prediction functions? Why not just choose the one that seems best? And you're suggesting the best would be, I'm going to say maybe you mean like the highest point of this distribution, the mode of the distribution. So there's a name for that, which we've discussed before. You guys remember from last week? The mode of the posterior is known as the map, the maxima posteriori, the map. So yeah, you could plug in the map. You could take the map W and come up with a single prediction function. Absolutely. That's fine. Yeah. But Bayesian gives us a distribution for starters. That's what we're looking at now. Good question. OK. Any more on these pictures? OK. All right, so let's drill in a little bit more to Gaussian regression in general and see let's see what these posteriors actually look like. So it turns out in this setting we can get a closed form for the posterior, which is very nice. So again, if our prior has a Gaussian, if we have a Gaussian prior, Gaussian likelihood, let's write X as our design matrix. Remember, a design matrix has the observation feature vectors in rows, right? X1 through Xn, there's n rows, d columns, there's d features. That's a design matrix, and y is the response vector. So the posterior distribution of W given D, if the world is nice to us, this should be Gaussian, and it is. So here I've written it out in pieces. So the posterior of W given D is Gaussian, with a particular mean and particular covariance, which I'm writing below. So take a look at this mu p for a minute. P is for posterior. Not exactly clear because P could also be for prior, but in this case it's for posterior. Does this thing look familiar at all? Like super familiar, right? OK, good. So one thing, before we talk about that familiar thing, one thing that's interesting here is that this sigma p gives us some measure of uncertainty in our W, in what we know about W. So if our posterior variance, sigma sub p, was, it's a covariance matrix. So if it had like eigenvalues, or if it were diagonal, it won't be, but if it were diagonal and the entries were very small, then this would be a small variance, and which would mean we're very certain about W. Okay. So posterior is Gaussian, yes. And what would the map estimator be? The map estimate of W is? Shout it out. mu of p, yeah. So the map estimate is the highest point of the posterior distribution. For a Gaussian distribution, the highest point is the mean. The mode is also the mean. All right. So the mean is mu p. So this is our mu p is our map estimate. That's right. Great. Now, let's make that connection to what you found so familiar explicit. So if the prior variance is sigma squared over lambda I is the diagonal, is the identity matrix, then the posterior mean is exactly this expression, which is exactly what we get from ridge regression, right? Where lambda is our regularization parameter. So that's an interesting connection. Yeah. Mu p, is mu p the MLE? Okay. What do you think? What? Okay. So how do you get the maximum likelihood? What does it mean to be the MLE? We're not maximizing mu given d, we're maximizing d given w. And remember, when you maximize d given w, it's just the likelihood model. There's no prior in the likelihood of d given w. It's just, let me go back to this. Here. So this is probability of w given d, right? This product of these two things. This piece is probability of d given w, and this is the probability of w, right? For maximum likelihood, we only have this likelihood piece. So when we maximize this, there's not even, well, in this case, there would be the lambda that shows up later is not even in this likelihood term. I have a better set of equations in a second. Okay, so let's back up a minute and look again at this posterior distribution. So we can write this in terms of the prior distribution and the likelihood, right? Posterior is prior times likelihood, proportional to the prior times the likelihood. So the prior, this is our prior on W, it's that zero mean Gaussian. And the likelihood is Gaussian. Okay. And now we've plugged in the special value for sigma 0. Okay. So if we maximize this over W, that gives us the map, right? That's the maximum posterior. All right. So if we maximize just this likelihood piece over W, that's the maximum likelihood. So they're not the same. Yeah, sure. So if we maximize this entire expression over W, that's the map. That's the maximum of the posterior distribution. If we maximize just the likelihood piece without the prior, that's maximum likelihood. How can we get maximum likelihood by how can we get towards the maximum likelihood from adjusting our prior? What can we change about our prior, maybe this variance? Yeah, as lambda goes to 0, this thing in the parentheses goes to 0. The exponent this thing goes to 1. So as lambda approaches 0, this posterior approaches the likelihood. Yeah.
Here lambda implies our regularization term, but if the ridge regression setup,
Yes.
Here we have to choose it beforehand.
Yes, that's true. So the interesting point was that, so let's come back to this question in a minute. Remind me. All right. Yes. Sigma 0 is the variance of the prior, which doesn't show up in the likelihood at all. This little sigma squared, that's the variance in the likelihood model. We assume we know sigma squared, that's right. OK. So lambda going to 0 makes the posterior go towards the maximum likelihood, or rather the likelihood. What's happening to the prior when lambda goes to 0? The prior has big variance? Gets flatter. Why? Because as lambda goes to 0, the sigma 0 gets really big. That spreads out makes the variance very large, right? So a very diffuse prior. As the prior gets more and more diffuse, has larger and larger variance, yes, it becomes more and more like just doing maximum likelihood. Right. OK. So great. So to find the map, we could also do the minimum of the negative log likelihood. Fine. And it breaks down into these two pieces, which is exactly the ridge regression objective function, right? Now, so there's this great question, which is, in ridge regression setting, we don't pretend that we know what lambda we should use. We have a validation set, and we tune lambda to optimize on the validation set. In this Bayesian setting, the premise was you just write down your prior, and that's it. And that corresponds essentially to choosing a regularization parameter lambda without even looking at validation data. That's interesting. And that's the case. So what does a Bayesian do when she doesn't know what the variance should be? Like, no idea. You could just guess something, but as we've known from our experiments with ridge regression, that tuning parameter matters. So what you can actually do is put another distribution on lambda. Hyperprior. For real. Another thing you can do is you can, and this is no longer a Bayesian approach, you can do what's called empirical Bayes, which is where you estimate lambda from the data in the sense of you find the lambda that gives your data the highest likelihood. It would no longer? Anyway, it would no longer. Yeah, that's right. If you use your data to help you choose lambda, that is no longer a prior in the sense that we mean. So that's a little bit sketchy. It's certainly not a standard acceptable Bayesian practice. Nevertheless, in practice, it's done a lot. So we'll explore this a bit in the homework, not for this model, but for the beta binomial model. Yeah. OK, great. Great questions. One thing that's nice about this, though, is that in this setting, lambda has a very natural interpretation. It represents the variance in our prior. So, we may have a very reasonable idea of what the scale of W should be. And so, from looking at this gives us a sense of how to set that regularization parameter. OK. OK. All right, so just a few more slides here. We've talked about posteriors. We've talked about coming up with our prediction functions for each W. We get a distribution over prediction functions. OK. So suppose we now want to apply our Bayesian setup to new data points. We've had our training data, and now we're deploying our model. We get a new input point, x sub nu. We want to make a prediction for y sub nu. What to do? All right, so first of all, we have a predictive distribution. probability distribution of y new given x new and the data d. So we're in the posterior setting because we're conditioning on the data, the training data d. All right, well, simple. It's just an integration problem now. Let's add in our theta. I've gone generic to theta instead of w. Sorry for that confusion. So put theta in the conditional and then multiply by the probability of theta, integrate out over theta. And that's how we can come up with the predictive distribution. OK. So for Gaussian regression, this comes out to have a closed form, which is very nice. Let's write that down here. So given a new data point, the posterior distribution for y, the predictive distribution for y given x, is again Gaussian. The mean is kind of what you'd expect. It's the posterior mean for the parameter of w, right? This mu p is all the way back from the posterior distribution of w, right? The posterior distribution of w has mean mu p and covariance sigma p, right? So mu p transpose x nu, that's our best prediction. And what's interesting is what's the variance that we're going to predict associated with that prediction. It's a Gaussian with a particular mean and a variance. So now it has two pieces. First, it has this sigma nu, the x nu, sigma p x nu. This comes from the variance in theta. This should be w, sorry, typo. This comes from the variance in w, our unknown parameter, our unknown coefficient vector. Because we have uncertainty about w, our predictions are going to have uncertainty, right? So that's what this piece comes from. The second piece, sigma squared, where's sigma squared from? Sigma squared is from the likelihood model. When y is generated, we add in Gaussian noise that has variance sigma squared. And there's no way to predict your way out of that. There's always going to be this baseline sigma square level of noise in the data. Even if we knew w for sure, we had an infinite data set size, this term, this variance would go to 0 because we have absolute certainty in w, but this sigma square will never disappear. Is that clear? OK. All right. Great. So what's nice when you have predictive distributions is you can now draw your prediction functions with error bars. Because we have for every x, we have a full distribution for y. So one way to write that, one way to draw that, kind of sketch that distribution is draw the mean of y for each x, that's this line, and then draw standard error bars or standard deviation bars around your prediction. So this is very nice that we have error bars now, or a margin of error, or confidence in our prediction. OK, any questions on this? That'll be it for Bayesian. All right, let's take a break. If you have any questions during, come up. See you in 10. All right. Who knows k-means clustering? Well, it's like a wave. Everybody. Good. Let's take a quick look to set it up. So we're going to talk about mixture models, Gaussian mixture models. But let's warm up with k-means. So here's some data, old faithful geyser data. We have a lot of points. Visually, they seem to come in two clusters. Algorithmically, how can we find these clusters? OK, that's the problem. Bless you. OK. So k-means, here's the algorithm. We first standardize the data. We'll discuss why later on. Choose two cluster centers randomly. Remind me to come back to this as an interesting question in and of itself. What's the next step after you choose two cluster centers randomly? That's right. For every point, you see which cluster center it's closest to, and you assign it to that cluster. So, whoops. There we go. This is the dividing line for which is closer to blue versus red cluster center. These are all the points assigned to this cluster. These are all the points assigned to this cluster. That's round 1 of our algorithm. OK, step 2. Now we take all the points in each cluster, find their mean, and move the cluster center to the mean. That's what's happening here. So we have new cluster center means. And now we iterate. For every point, we assign it to the cluster center it's closest to. So all these points are now going to get attached to this cluster center like that. OK? Iterate until convergence. That's k-means, clustering. Why did I say it's actually an interesting problem in and of itself to choose cluster centers? OK, if you do it well, like close to where they should be, it cuts down on your work a lot. Yeah. OK. And I would claim it probably doesn't matter too much in this setting. Well, maybe a little bit, but what happens in really high dimensions? In really high dimensions, it's hard to find points that are natural cluster centers. So the safest thing to do in general is to just choose random data points to be cluster centers and not bother with random points in the space. That ensures that your cluster centers are at least close to some points, right? And not way out in another universe. OK, good. So why do we have to standardize the data? Well, here's an illustration of the result of k-means clustering when we don't standardize the data. What's going on here? Visually, why are these points blue over here? It doesn't seem like this point should be in this cluster, in the black cluster. What's going on here? Look at the scale of the y dimension. It's going by tens, where in the x dimension it's going by ones and much bigger. So any small difference visually in the y direction is contributing a huge amount to the distance. Okay? So essentially, this y distance is really important. It's more or less just separating along the y-axis. Right? So it's a good idea, if you don't have any prior opinion on how important each dimension is, to rescale to all be the same units. And then visually, this fixes the problem. So always important to think about the scale of your data. Yeah?
Makes sense.
Yeah, so would it ever make sense to have an opinion? Sure. So more generically, right now, we're using Euclidean distance for distance. You could use any distance metric you want. And you could define the distance metric to represent what you think is a good measure of how different two things are. So maybe there's a particular feature that naturally has a huge scale. It's in thousands and everything else is in tens. But you don't think that that feature is really very important and should not contribute very much to the overall distance, then shrink it way down. But if you think it is relatively more important, then keep it large. It's just, you control the distance metric. Yeah. Clustering is very much the way you set it up determines what you get out of it. OK. Any more questions? OK. How do you evaluate how good clustering is? Great question. So there are, just for this type of algorithm, there are ways people have come up with that to these people sound like good ways to evaluate. Like, for instance, how spherical are the clusters? That might be, you may want your clusters to be more spherical instead of like spread out and straggly. Yeah. OK. I don't know that method. Do you want to elaborate on it, or? Okay, so you're saying that if you have some auxiliary variable that's like a class label, then you can look at how that auxiliary variable distributes among your clusters? Okay, but then you lost me after that. But that's, okay, we could talk about this later. It sounds pretty interesting. Maybe we can present it next week. All right. Okay. So k-means can, the next way we're going to approach clustering is to make a probability model to generate the observations, and then there's a natural way to evaluate it, which is kind of holding out some data and seeing how, using likelihood to evaluate how likely some holdout data is under your clustering model. We can come to that later. Oh, you're just saying that you think it's a good idea to initialize your algorithm with centers that are far away. I don't know if that's the right intuition. I'm not sure. I don't know that. I wouldn't predict that. My best guess would be to randomly select points from your distribution and just go, and then run it a few times and see which clustering you like the best. Yeah, seriously, clustering is very. Yeah, go ahead. So the question is, can you learn the number of clusters? Okay, so can you learn the number of clusters? Can you learn your distance metric? All of these things can be learned if you have a way to evaluate how good your clustering is, right? So without a very concrete way to evaluate your clustering, you have nothing to do. You just look at it and hope for the best. So this is not very in concordance with what I presented on the first lecture, that the core of machine learning is an evaluation thing. So clustering on its own I'm not too fond of, but what if you use clustering to give you a new feature? How would you do that? Suppose you have an actual prediction problem, you cluster your inputs, and then you could take the cluster labels as features for your linear regression. That's interesting because clustering is a highly nonlinear feature that's discovering perhaps some structure in data, or maybe it's discovering garbage. But now you at least have a way to evaluate it. You see how well do the features help your prediction problem. Okay, now clustering seems interesting again because you have a way to evaluate it. Okay, yes? Okay, so the question is, does the algorithm always give you the same clusters if you choose different starting points? No, it does not. It absolutely does not. It does not converge to any kind of global optimum of clustering. Okay. Say again. The result of the clustering is, of course, based on the data set that you cluster. Yeah. So it depends what you mean by clustering. Let's come back to this question in a minute. Yes. Well, I have to write down the questions then. Okay. Different training sets. And I had one I wanted to say, loss functions. Yes?
So the evaluation for clustering is just compare the data, right?
No, there's lots of ways to evaluate clustering, but there's not necessarily a most natural way to evaluate it. There's not like, when we did regression, it seemed very natural to say, let's use square laws, or we could use median, or we can use some other things, but there's some natural things. For classification, 0-1 loss, right? For clustering, there's lots of papers written on different ways to evaluate clustering. I'm not going to talk about those. I don't personally find them so compelling, but it's maybe worth a look if you.
It's for high dimension, very high dimensional data. We can't, there's no way to just like that. They went there, I mentioned it.
How do you actually look at clusters in high dimensions?
Or yeah.
Yeah.
Evaluation, is there? Or
Yeah, you can. There's different methods to look at low-dimensional projections of the data. So you could do PCA and take the first two components. Or there's lots of different ways to do low-dimensional looking. But no, it's not trivial. That's a weird thing to evaluate high-dimensional clusters when you can't look at them. Yeah. Okay. Yeah.
Does it make sense if you have data that has lots of attributes to split it such that you're clustering twice and you're trying to get two sets of labels?
So can you cluster on, say, suppose you have features that maybe naturally have two groups or something? Or no, you want to randomly split the features into two groups?
I would split them according to.
So if you have, so for instance, you have a set of features and they naturally split into two groups, could you cluster on each set of features separately? Sure. And that would give you two different clusterings.
That would give you a fundamentally different result than just one clustering.
One clustering with more groups. So it all comes down to, instead of thinking about features, which features you include, why don't you just think about it as different distance metrics, different ways to measure the distance between 2 points, right? So in one way, in one distance metric, you only include features from one group, and the other you include features from the other group. So the question is basically, with different distance metrics, and we're just doing, you're saying make two clusters?
No, I'm sorry. I run the algorithm twice. One on one set of features, one on another set of features. So I get two groups of labels for each.
Okay. And then, so you're saying run clustering with two different distance metrics or two different sets of features. You get two different two different clusterings, and then.
Just wondering if that's any different than just.
And is there a way to get the same same clusters, like if you took the intersections of all those clusters or something?
I'm just wondering if it's any different than just running it one time with all the attributes of more clusters.
Okay. Okay. So. Okay, first clustering algorithm is this and this. Okay?
I guess I was thinking more like you had four features. You wanted to sort of, I know you can't draw something in four-dimensional space, but you could do two and two dimensions.
Okay, I'm not. Okay, I just did that as a matter of fact, except with 2 instead of 4, right? So this is clustered only based on this feature, and this is clustered only based on the other feature. So I'm 2 dimensions before you, okay? Now, so we have 2 different clusterings, each giving 2 clusters, and it sounds like you're asking if we ran clustering again with 4 clusters and maybe a different distance metric, can we end up with, you want to do the intersections? What do you want to do all combinations of clusters? All right, so I think you're basically asking, can we end up with this? Maybe.
I'm not saying.
I don't know. I'm not sure. Okay. Evaluation. That was also your question. So as I was talking, I thought of another way to approach it is that although k-means was presented as an iterative algorithm, one can also look at it as, I took those slides out, unfortunately, as minimizing an objective function with an iterative optimization method. Okay, so you can actually look at k-means as minimizing an objective function. And in that case, you could compare different clustering methods by which is a better method, which, but once you define your loss function, then that's kind of, then you can compare the number of clusters you have by how big the loss is on new data, for instance. Okay, here's the question. Here's the question that's coming. So on your training set, suppose I have a loss function that we're minimizing to get, yeah, and what would the loss function be? It's very obvious. Yeah, the loss function that k-means is trying to minimize is the sum of the square distances between every point and its cluster center. That's very natural. Okay. Now, if we increase k, the number of means, what happens to the loss? It can only go down, right? It will never increase. Okay. So if we're just looking at training loss, then of course you will always try to make more clusters. Okay. Yeah. What if we split our data and we have some training, some holdout data that we did not use for clustering? Okay. Now can we evaluate that same objective on the test data? Well, think about it. Can you do it, first of all? I want you guys with me. What's an issue? No, you cluster on the training set, you get your cluster centers. Those are the clusters. That is what you learn in clustering. You learn the cluster centers in k-means. Yeah. Okay. Now we get new test points. We have our cluster centers learned from training, k of them. And you know how to assign our test points to clusters? Yeah, find the cluster center it's closest to, easy. Okay. And now we could do sum of square distances between all of our test points and the cluster centers, right? Okay. Test error.
More k is still less error.
Will more k always be less error?
You have more probabilities.
Yeah.
So in that case, you cannot choose function of k.
Yeah, so this gets, okay. So that improvised approach was not successful in choosing k. Good effort. Okay. So, any more? No. Oh, did we address your question about different training sets? Okay. No, did we answer it already?
Yeah, but I am thinking that what if it's a subset of the
So can you do bagging on clustering? So what's the one operation you have to be able to do bagging?
Like I choose parts of the training set in clustering and I choose another subset.
Yeah, so for every time you do clustering on a subset of your data, you're going to get a different set of cluster centers. And for bagging, you need to be able to combine those cluster centers into the final set of cluster centers. So I don't know how you do that. That's, yeah, I don't know. What?
Cluster of we can do clustering on the central.
Cluster the cluster centers. Okay, that's an interesting algorithm. You guys should write a paper. 2 authors, good job. All right. So failure cases for k-means. Here's a failure case. So this is not 2 different pictures. This is all one picture. These are the points spread out in space, and our algorithm will get stuck right here. So 2 cluster centers here and 1 here. If you work through the steps of recentering the cluster centers and reassigning the points to centers, you'll see that it will get stuck here, but this is obviously not the best. We should have 1 cluster here and 2 here. So k-means can get stuck in suboptimal positions. Sorry, you just have to, the best you can do is restart at different initialization points. Yeah. Okay. But now the loss function helps, because we don't know if it's suboptimal, but we can at least detect if we're doing better or worse with the same number of clusters on the same data, because we have a measure of the performance. Start with different random initializations and see what the loss is that you end up with, right? Okay. All right. I'm not a fan of k-means clustering because I don't know how to evaluate it in any way. So I'm a much bigger fan of probabilistic approaches where it is much more natural to evaluate. So Gaussian mixture models is a very popular probabilistic approach. Let's talk about that. All right. So this is, in general, a probabilistic approach to clustering. We make a generative model for the data. That means we describe how data could be generated. Suppose we have k clusters, and here's the key step. For each cluster, we have a probability density for that particular cluster. All right? So to generate a new point, so we're going to discuss how would we actually generate the data that we're observing. This is called probabilistic modeling. We first choose a random cluster of the k clusters we're talking about. And then we take the distribution associated with that particular cluster, and we sample a point from it. Here's a picture. Here's 3 clusters, and we're going to assume each cluster has a Gaussian distribution. And for now, let's assume we know the means and the variances. All right? So to generate a point, we first choose one of the 3 clusters with, say, equal probability. And then we would choose a point from each of the distributions of these 3 clusters. So to get to this blue point, we would first have chosen this cluster, and then drawn a point from this Gaussian distribution and ended up there. So this is how data would be generated by this. This is called a Gaussian mixture model. All right. So I've described how data is generated. I haven't said anything about clustering yet, so don't worry if you don't see the connection. Is this clear? Okay. All right. Let's get some parameters down. These are parameters. Now we're back in frequentist setting for Gaussian mixture models. You can do it Bayesian too, bless you. So cluster probabilities, we have k clusters. Let's call them pi 1 through pi k. We have k means and k covariance matrices for each of the cluster covariances. So for now, let's assume that we know all these parameters. So we know the generative model, and let's see what we can do with it. How we learn it, we'll come back to later. So I claim that once you know these parameters, we can kind of back into a clustering from this model. So first of all, remember these guys? It's a Bayesian network. And x, this is just showing that we want to write the conditional distribution of x given z, and then the marginal distribution of z. So the joint distribution of x, and what are x and z here? Let's recap. So z is our cluster center. X is our actual point in space. Okay. So what's observed if we're observing data? We observe x, and we don't know what cluster it came from, z. So x is observed, z is not observed. Let's write down the joint distribution of x and z just to make sure we know what we're doing. So x and z, we can factorize like this always. This is no independence. And now we write down pi z, that's the the probability of being in label z, and this is the conditional distribution of x given that we're in cluster z. Okay. Great. So z is basically the cluster assignment that we want to figure out. All right? So in the generation process, we're figuring out what cluster a given point is in, and then we come up with the point. So what we want to figure out is what is the z corresponding to a particular x. That's the name of the game. Okay. So this is called a latent variable model. So we observe x, we don't observe z. That's the cluster assignment. The unobserved thing is called the hidden variable or latent variable. And a latent variable model is a probability model for which certain variables are never observed. If you heard of LDA, latent Dirichlet allocation, that's another example. So Gaussian mixture model is a latent variable model. And then the Gaussian mixture model inference problem. What's the inference problem? The inference problem is we observe x and we want to know z. we assume we know all the parameters of the model. That's what inference is. Okay. So let's see how we would do that. So we know the full joint distribution of x and z. We want to know the cluster of z. Sure, just take the conditional distribution of z given the observation x. And that gives you a distribution over clusters for a given point x. And that could be our end game. That gives us what is called a soft cluster assignment, right? So for any given point x, it's going to have a probability distribution over each of the clusters it could be in. That's fine. It's called a soft assignment. How would we get a hard assignment? A single cluster assignment for a particular x. Yeah, just take the z that has the highest probability. That's a hard assignment. Great. Those should be in max, shouldn't it? So if we have the model, clustering is easy. Inference problem is easy. What's left to do is learn the model, learn what all those parameters are. Okay. So let's back up a second so I can tell you guys what mixture models are in general. Well, yes, okay. So the marginal distribution of x. X is what we observe. So if we want to talk about like the likelihood of the data, it's the likelihood of x, not z. Z is not observed. That's not part of our data. X is our data. So we want to figure out the likelihood of x. Then for learning, we can maximize the likelihood over our parameters. So to get the likelihood of x, this is a single observation x. We can just take the joint and marginalize out over z, which we've done before. So marginalizing out over z, it becomes a pi of z. It's a distribution over clusters, right? So sum of pi of z is, of all these pi z's, that's 1. And each of these is a Gaussian distribution on x. So this is a convex combination of distributions. That's what a mixture model is. It's when you can write your likelihood function or density or probability as a convex combination of other likelihood functions or convex combinations. All right. It's a formal definition. Okay. So in the Gaussian mixture model, every data point x has a mixture distribution. It's a mixture of the three, in our case, the three Gaussians that it might have been drawn from. All right. All right, so the learning problem for Gaussian mixture models. So now let's back up to, let's expand to not just one x, but now we have a training set, x1 through xn. That's our data, drawn from a Gaussian mixture model. And these are all the parameters we have to estimate for a Gaussian mixture model. It's a lot. So, but once we have the parameters, we're set. That's great. So there's a lot of ways to do Gaussian mixture model fitting. Maximum likelihood was the most popular one for a very long time, but just recently, this even older method of statistical estimation called method of moments has taken the lead as a great approach to do Gaussian mixture models. So go ahead and look up method of moments or spectral algorithms for Gaussian mixture models. Very, very interesting stuff. But we're going to go the tried and true maximum likelihood method. So write down the likelihood function for our data. We can try. So likelihood function is, of course, a function of the parameters. We're going to maximize this over the parameters. Now we have endpoints, and they're independently generated. So it's just the product of these probabilities or likelihoods of x. Get this product of this sum. This is the mixture formulation of xi. Okay. And what we can do is take this is the likelihood. We can take the log likelihood and also consider that. So the log, as usual, changes this product into a sum. And then we have this sum, then we have the log of the sum. And that's an issue, because the log of the sum doesn't simplify nicely at all. And in some sense, in some mathy sense, this is the problem with learning Gaussian mixture models. And this is why we have to use some new approach, or at least it's preferable to use some new approach, this EM algorithm, which we're going to discuss mostly tomorrow. Okay. All right. So here's the let's look again. This is the log likelihood for a Gaussian mixture model. Let's compare it to trying to get a sense for why was it easy for just Gaussians, but it's really hard for a mixture of Gaussians. So let's look at the log likelihood for a single Gaussian. All right. So we have a bunch of data points, x1 through xn. Each is Gaussian distributed. The log likelihood is the sum of their log likelihoods of each of the individual points. Great. And expands out very nicely. What's happened here? So what's the first interesting? So what's the Gaussian density look like? It's got some constant term out front, and then it's e to the something, right? So this log of the Gaussian, that log is going to cancel with that exponent. And that's why we are left with this very simple sum of quadratic forms. There's no e's in this expression, right? This is a very easy thing to deal with. We don't have that same simplification for the Gaussian mixture model because we'd love this log to cancel out all the exponents in the Gaussian here, but the sum blocks the log from doing that cancellation. So this is why the Gaussian mixture model likelihood is so much more difficult to deal with than a single Gaussian. Is that clear? Cool. More nods than ever. Great. Okay. And in particular, there's no closed form for the MLE for Gaussian mixture model. All right. So before we get into learning, or statisticians might call it estimation, estimating the unknown parameters, I just want to point out a few issues with Gaussian mixture models, just that you should be aware of. So I suppose we've done some learning. We found some cluster parameters. Suppose we've found a minimum of our likelihood, and we've chosen those parameter values. Do you think that that minimum is unique? No. Someone thinks it's not unique. Why would the minimum of these cluster parameters not be unique? Two Gaussians. Okay, so just rather vaguely saying there might just be more than one thing that maximizes the likelihood. I think there's a very obvious particular way that there'd be multiple, I've been saying minimum, multiple maximum of the likelihood. Okay, so for certain data distributions, like you're saying it may not matter at all where you put, like if it's uniform or something. Okay, maybe, not sure. So how about, so suppose mu1, that's our first cluster center, is over here on this side of the page. And mu2 is over here on this side of the page. Okay. What if I switch mu1 and mu2? Would anything change in the likelihood? No, right? So there's this, at the very minimum, there's the non-uniqueness because you can permute your assignments of clusters to mu1 through mu k, and nothing will change at all. So this is called an identifiability issue. It's not an identifiable parameterization because, okay, so that's one simple issue you guys should be aware of. Not a major issue in practice, but okay. All right, here's a more interesting issue. This is something that we've kind of discussed before, but consider this data set and a mixture of two Gaussians. So I claim you can always get a likelihood that goes to infinity, which is kind of sad. Do you see how? Yes, but don't want to say. Oh yeah, right. The Gaussian here I've hinted at it by kind of putting this Gaussian on just one point. As this variance goes to 0, the likelihood goes to infinity. So what does that even mean, maximum likelihood? There's nothing special about this data set at all. So the actual maximum likelihood for Gaussian mixture model is always infinity. There is no maximum likelihood. Okay. It's okay. In practice, it's not an issue. In practice, it's usually not an issue. And you'll see when it's happening. So, and then if you want to be very careful about it, you can regularize your variances so that you penalize if they're too small. The clean way to do that is with a Bayesian setting, where you put a prior on your variances and that sort of thing. But it's also at least important to be aware of this issue with maximum likelihood for Gaussian mixture model. In practice, you don't end up at these kind of extreme cases. Okay, great. Okay, so I'm talking about this EM algorithm that we're going to need to apply to Gaussian mixture model. And then the question is, do we really need it? What about the techniques we already know? What do we know? We know gradient descent. We know stochastic gradient descent. Here's a function. Can we just take the gradient and do it? And follow the gradient to maximize the likelihood? Yes, you can try this. You can. There's a few things you have to be careful of. So for one thing is, in our parameter space is a matrix, sigma z, right? So sigma c has to have, it's not just if our dimension is d, this is not just an arbitrary set of d squared numbers, right? What do we need the entries of that matrix to? They have to have certain properties as a matrix. Yeah, it has to be a covariance matrix. Not every matrix is a covariance matrix, so you can't just arbitrarily maximize this over all the elements of the matrix. So we need some way to keep where we are in parameter space so that all of our matrices are actually symmetric positive definite, so that they will actually be Gaussian distributions and not. Yeah. Okay, so there is a clever way to do this. So here. Turns out, well, this at least gets you positive semi-definite. This is from homework 4, maybe. Remember, every symmetric positive definite matrix can be written as a matrix times its transpose. And conversely, a matrix times its transpose is always positive semi-definite. Okay, so what if we parameterize every covariance matrix by another matrix M, which is kind of like its square root-ish? Then we can let M move freely in space, and the corresponding sigma will be positive semi-definite. That's fine. If you really want positive definite, you can factorize it more and make sure that diagonal elements are strictly bounded away from 0. There's ways to do that too. Okay. All right. So I have a little bit of time left. Let's start looking at the EM algorithm for Gaussian mixture model, and we'll finish it up tomorrow. And more interestingly, tomorrow we're going to talk about the general EM algorithm, which if you want to go more deeply into like graphical models and learn about variational methods, this is a great intro to all those things. EM algorithm is, as we'll present it, is a very simple variational method, which is a popular way to do inference on models that are, or learning and inference in models that are intractable. Okay. Questions anyway? Okay. All right. So first, this is the Gaussian model, not a mixture model, just simple Gaussian model. And have you guys calculated on your own at some point? Everyone should at one point in their life prove to themselves that the maximum likelihood estimators for the mean and the covariance matrix for Gaussian model, wow, sorry. Looks like this. This is just the empirical covariance matrix and the empirical mean. So that's the MLE for a single Gaussian model. So for Gaussian mixture model, if we knew the cluster assignment of every point, then figuring out the distributions of each cluster is trivial. We just find the maximum likelihood estimate of the Gaussian component for each of the points in that particular cluster. So if we knew the cluster assignments, it'd be easy. Okay. And remember, this is almost already reminds us of the k-means approach, where we randomly made cluster assignments initially, and then we find our cluster centers, and then we alternated back and forth, right? So that was because once we knew our cluster assignments, it was easy to find the means of all the clusters. So by analogy, here, once we know the cluster assignments, it's easy to find the Gaussian distributions that best fit the points in that cluster. Okay. So here we're probabilistic, so let's introduce some new notation, which is, we discussed this before. This is the probability distribution on the cluster given for the point x. So for xi, this is the probability that cluster is cluster j. All right, so let's write that for convenience, gamma sub I superscript j. So the I is the point and the j is the cluster. And gamma ij is the probability that xi is in cluster j. Clear? How can we do that? Because we've assumed we know what the parameters of the model are. Okay, that's gamma ij. So this is called, we can call it, just to kind of build our intuition, the responsibility that cluster j takes for observation xi. Okay. And just working out, plugging in our densities, we can get an explicit formula for gamma ij. These can be calculated very easily. And this constitutes our soft assignment for the point xi, right? Great. Okay. So let's write n sub c. So n sub c is the sum of gamma ic summed over the points I. So this is like the sum of the probabilities that each of all the points being assigned to cluster C. That has another interpretation, right? Sum of probabilities of events related to expected value, right? So this would be, in some sense, the expected number of points that are assigned to cluster C. So it's like, we have a distribution for every point for what cluster it's assigned to. If we drew randomly a particular assignment according to that distribution, and then we added up how many were assigned to a particular cluster, the expected number of that count, that's the sum of these probabilities, n sub c. It's an easy calculation. Okay. All right. So here is our EM algorithm without derivation. That comes tomorrow. So we have our parameters. E step, the expectation step. Evaluate the responsibilities of each point across all the clusters. So compute all the gammas, right? That gives a soft assignment of each point to all the clusters. That we can compute straightforward. Okay, what's next? So now we have the soft assignment to each of the clusters. If we had a hard assignment, it'd be trivial. If we had a hard assignment, then we can fit the clusters to the hard assignment and, golden. And we can iterate. We have the soft assignment. So we get something that's a little bit different. This should look very familiar. It's very similar to the MLE for Gaussian distribution. But now we have this weighting. So what's happening here? We're summing over I from 1 to n, so we're summing over all the data points. And we're computing the mean of those data points, but it's a weighted mean. It's weighted by the probability that each point is in cluster C. So to find the mean of cluster C, find the weighted average of the points, where the weighting is proportional to how probable it is that point is in cluster C. Seems intuitive, right? Okay. N sub C is the interesting. There are n things in the summation, that's true. But we want the average of these xi's to be a convex combination. We want it to be a weighted average. In a weighted average, we have to make sure that our weights sum to 1. Now, if we bring the NC in, we'll see that the weights are actually gamma IC over NC, and those will sum to 1 because NC is exactly. NC is the sum of the gamma ICs. Yeah. So in a weighted average, our weights must sum to 1, so that should be NC. Yeah. And very similar story for the covariance matrix estimation. Okay. So now we have our mean and covariance estimated parameters. The proportions on each cluster are done very naturally from this expected number of points assigned to each cluster divided by the total number of points. And this is an iterative algorithm. So we have our parameter estimates, and then based on those new parameter estimates, we get our cluster responsibility assignments, and then we iterate until the log likelihood converges. What's the log likelihood? We can compute the log likelihood of our data given this setup, given the parameter values. Okay. Yes. E stands for expectation. M stands for maximization. There's not really a way to see why expectation has anything to do with this E step. The M step, maybe you can see because there's this kind of maximum likelihood estimation. What we'll see tomorrow is that the EM algorithm is an optimization method for the likelihood function. So this is an iterative method to find at least a local maximum of the likelihood for the Gaussian mixture model. All right, that is it for today. We'll come back to this tomorrow.